Another way to build a heap is to convert an existing array that is not in heap form into a heap. To do this, we begin in the middle of the array. We're going to see that the middle of the array is the point at which nodes start having children underneath them. And so we will begin at the midpoint of the array and we will move towards the root. Okay, so we know that the root is at element 0, so we will move toward the root from the midpoint in the array. And what we will do is we will call heap down for every one of those nodes that we encounter on the path from the midpoint to the root. We will call heap down on that node. Now, here's the pseudocode for Floyd's algorithm. This is how this is done. And the key thing to remember here is that when we call heap down, we will heap that node all the way down. So when we return, we have heaped the node as far down as it needs to be. So it's important to realize that this is not just a single swap, but it is a complete heap down all the way to the point where the node belongs. Okay, so the array after this, the execution of this algorithm will possess the heap order property. We will do a max heap example. The min heap example is obviously symmetric to this one. Let's take a look at the array. So let's say that somebody hands us this array and they ask us to put it in heap form. So the first thing we can do is let's try to envision this array as a binary tree. And so this is what it looks like. It's got 11 and then 3 and then 9, 5 and 7 and 14 after that, and then 8 and then 4. As you can see, this is neither a min heap nor is it a max heap. 11 is greater than both 3 and 9, but 3 is not greater than 5 and 7, so it's not a max heap. 11 is, and by 11 being greater than 3 and 9, it's not a min heap. Okay, so we have this array. This is an array, so n here is 8. Okay, the elements are from 0 to 7, but that's 8 elements. And so we will find the midpoint by n, or by size, minus 1, integer divide 2. Okay, so this is 8 minus 1, which is 7, integer divide 2, which is 3. Okay, and so this is the point at which we begin, and we will move toward the root. We will heap all of these nodes down. As has been mentioned, this particular node is the first node in the upper half of the array that actually has a child. Okay, so 5 is the parent of 4. Okay, and then we must keep in mind that this is a max heap. So we would like the maximum value to end up at the root. And so we begin here and we heap 5 down, okay? And 4 is not greater than or equal to 5. So 5 is already in its correct place, and we've done this index, okay? We will then we will decrement the index and we will go to the 9, okay? And we need to heap the 9 down. And again, recall that this is a max heap. It turns out that the 14 is greater than or equal to the 9. The 8 is not. So we need to swap the 9 and the 14. Okay, and so that's going to put a 14 here and the 9 here. Okay, and then as we do this, the tree now looks like the 14 is here and the 9 is here. So let's redraw. It's 11 and the 3, now the 14 and the 5, the 7, the 9 now, and the 8 and the 4. And we're continuing to try to heap down the 9, okay? And the 9 is all the way at the leaf, so the heap down terminates, okay? It's only at that point that I decrement, that I've actually done this one, and I will decrement and move towards index position 1, okay? And so we ask ourselves here, let's heap down this 3. Well, both the 5 and the 7 are greater than or equal to 3, but since this is a maximum heap, we will take the 7, which is the greater child, and swap it with the 3, okay? And so the 3 and the 7 giving us this tree. Right, we swap these two, 9 and the 8, and finally the 4. Okay, and at this point we swapped the 3 down. We're trying to heap the 3 down. We would continue to try to heap the 3 down, but it's already at the leaf, so that heap down terminates. Okay. And we have now decremented, so we decrement one more time, and we're now here at the 11. Okay, so we're here, and we're going to try to heap down the 11. We take a look at the 7. It is not greater than or equal to the 11, but the 14 is, so we make this swap. Okay, and then so we will scrap that. That'll be the 14 and the 11 will change places, and that will give us this tree. Okay, so let's put the 14 here and the 11 here. That's going to be this tree. And the 4 is here. Okay, and so we were at the root and we were heaping down the 11, so we must keep trying to heap down the 11 to make sure that there are no additional violations. Well, both the 9 and neither the 9 or the 8 are greater than or equal to the 11. So we have restored the heap order property, and as we look at our array, it is now in heap form. 14 is greater than both 7 and 11. 7 is greater than 5 and 3. 11 is greater than both 9 and 8, greater than or equal to. And then the 5 is greater than or equal to the 4. And so we have a tree that is a complete binary tree. The last row is aligned from the left, and it has the heap order property. And so this that began as an array is now a heap.